Okay, so thank you and welcome again. So this lecture will be about energy autonomous embedded systems, as just mentioned. As you might notice, this is of course a technology lecture, but I was asked to do as popular science as possible. So I will try my very best to keep you involved, even if you're not from a technological field. So what I would like to start with is to ask all of you to imagine a computer. And this, of course, would have been much easier if we were in a live lecture or in a lecture room in the same place. But I assume that many of you thought about something like this, a personal computer, maybe a laptop instead. So some sort of personal computer. But these computers, so personal computers, are actually just a very small fraction of computers around us. In fact, if we look at statistics, we find that about 98% of all computers around us, they actually look quite different. They're computers that we would, in our field, call embedded computer systems or embedded systems. So these computers are embedded or integrated in some other type of system. So you could think about your washing machine at home or your dishwasher, which you would certainly not imagine, hopefully, at least from my point, to be made to be a computer. But of course, at least nowadays, these type of devices or systems, they actually have computing systems integrated. So they have these small types of computers that have very specific purposes to be performed. But they're still computers, and they're actually the majority of computers. So how did we get here? Why do we have so many computer systems? The ones of you that are in a technological field, you probably have heard about something called Moore's Law, which is named after Gordon Moore, who was the co-founder of Intel. And I suppose that many of you might have heard about Intel. It's one of the largest computer processor companies in the world. So what is Moore's Law about? Well, Gordon Moore, he mapped basically computer systems, processors over time, and he found that there was quite a systematic relationship. So what he observed is basically what you can see here in the graph, that basically over time, so in principle, every second year, you could say, the number of transistors doubled in a processor, more or less. And if we think about that, the transistors is the basic building block of a computer or a processor, defining its performance, simplified at least, we can basically say that every 2 years, you can basically buy a new computer that is double as fast as your previous computer. And that is, of course, basically how we observe Moore's Law, maybe at least in personal computing quite a lot, so that we can basically think about that, okay, every 2 years I can buy for the same amount of money a new computer that is double as fast. But if we can do that, we can also turn it the other way around. And we could actually formulate it that, well, if we could buy a computer that is double as fast for the same amount of money every 2 years, well, then we could buy the same performance computer after 2 years for half the cost. And this is much more interesting from my perspective here in this lecture, at least from embedded systems point of view, because that is, of course, what enabled that we can have very low cost computers over time, and basically integrate these kind of computer systems at marginal cost increases into everyday objects, basically leading us to this point where we have all these computer systems, embedded systems in different types of devices around us. If we look a little bit into the future from that, or basically already started, this trend of that we get more and more computer systems around us, this will not stop. In turn, basically, this will probably increase, at least what we expect right now. So a couple of you, or many of you, might have heard about the term the Internet of Things, where we basically talk about just this idea of bringing basically computer systems, connected computer systems, to more and more devices, to more and more systems. And now we're not only talking about electronic systems or mechanical systems, but we talk about biological systems. You could think about having computers integrated in yourself, so to speak, right? You could think about having computer systems integrated into nature in order to obtain information and to process that information for some sort of benefit for society, hopefully. Right? So if you look into reports on this by large companies, then you often find a number of computer devices in the order of billions of devices. So we talk about billions of new type of computing devices, you could say. Many of these will be small-scale embedded systems. And of these billions of devices, or probably at least billions of devices, I'm quite interested, particularly interested into the ones that we either cannot or do not want to connect to the power grid to supply them with electrical power. And this could have different reasons. This could be because the device itself is mobile. Imagine you have something that you wear on your body, for example. It's difficult to connect this to a power grid with a cable. So there are different reasons for this. Or it could be that we just do not want to connect them to the power grid because that would be too costly. For example, it would require an infrastructure that is too costly or infeasible to do. So for these devices, then, if we cannot connect them to power grids, we basically have nowadays the main alternative would be that we use batteries to supply them, which have negative effects on their own. If we have billions of devices, we would have billions of batteries, which at some point have to be recycled, which actually turns out to be not so super easy to recycle in an efficient manner. And it also costly to replace these batteries or to recharge these batteries. So instead, I'm interested in basically, as the name of this lecture says, energy autonomous systems. And for this, we use a technology that we call energy harvesting. So for the rest of this lecture, I would like to basically follow this outline, more or less. I will start basically quite simple and try to look at what energy harvesting is. We'll then go over a little bit into what components do you need to build an energy harvesting system. And then we go into, I try at least to go into two concrete examples of energy autonomous or energy harvesting embedded systems that we have been working on here at Mid-Sweden University. And then I will conclude with some challenges and an outlook, you could say. So if we start by looking at what is energy harvesting, right? What do you do if you don't know what it is? Well, of course, the first thing you do is you go to Wikipedia, right? So if we look at how the Wikipedia article on energy harvesting starts, at least, we can read that energy harvesting is the process by which energy is derived from external sources, captured and stored for small wireless autonomous devices like those used in wearable electronics and wireless sensor networks. So now we don't have to take this completely apart, but basically what I would like to highlight is two things, right? So what we can take from this is we're talking about external sources. So basically the energy that we need for our device comes from some sort of external source, and I will come back to this, what we mean with this. And the other thing which I will come back to quite a lot is we talk about quite specifically small wireless autonomous devices. So we do not talk about powering everything with energy harvesting, but we actually talk about quite specific types of applications. And I will come back to that, why we talk about that and why this limitation exists. We could think about this from a different point of view, right? So when I was a kid, now I don't want to talk too much about the bicycle at all, but basically I want to talk about this part, right? So when I was young, basically every bicycle had something like this, right? A bicycle dynamo. So I suppose many of you have encountered this and remember how unpleasant this was as a kid to bicycle. You never wanted to put this on because it creates some resistance, right? But this is actually quite an interesting example of well, maybe not really energy harvesting, but the same concept, you could think, right? The important thing here is that, well, you have a specific application, and in this case, this is the light, right? You want to use your bicycle when it's dark, so you want to turn on the light. For turning on the light, you need electricity, and well, where should you take the electricity from, right? Nowadays, most bicycles, I suppose, use batteries, which I probably have argued for so far that is maybe not the best option. But this was actually quite an elegant solution, right? Previously, that well, I need electricity. I don't have electricity. How could I get electric energy? Well, I look for other energy sources around me. Well, what do I have? Well, I have, for example, a rotating wheel, right? This is some sort of kinetic energy. And if I could then use some sort of device, in this case, this dynamo, that could convert this kinetic energy that is close to what close to the application where I want to have the energy to, then I can convert it and provide my lamp, in this case, with electricity, right? Maybe one small comment here to add is this looks, or this could be quite simply understood as some sort of renewable energy generation, right? I mean, we know this from large scale. We know wind power plants, we know photovoltaic power plants, maybe hydropower plants, right? They basically use something very similar, right? They look into, okay, there is an energy available in some form around the application, or around the plant in this case, and we use that to convert that energy into electricity, right? But there's quite maybe a small difference, you could say, from the wording, but a quite important difference, and that is that energy harvesting, when we talk about energy harvesting, we talk about specific functions that need to be powered. So in this case, we talk about a specific function that needs electricity, in this case, the light. We do not talk about generating as much energy as we want, because, well, if we would do that in this case, this would actually have quite negative effect, and that means that you would break your bicycle and you can't cycle anymore, right? If we look at some other examples where we can find energy harvesting systems in our environment, maybe more modern examples, I suppose many of you have seen these at least. The first ones, the pocket calculators that could be, for example, powered by a small photovoltaic panel here. So basically powered by the ambient light around you. Quite similarly, you have other devices that could be powered by photovoltaics. For example, this computer keyboard that basically would run eternally without ever changing the battery, of course, until it breaks, right? But there are other applications that maybe some of you haven't seen. So there are, for example, pocket watches, or these wrist watches, basically, smart watches. In this case, this one is powered by a thermoelectric generator. So it's basically powered by the temperature difference between your skin and the environmental ambient temperature. We can find mechanically powered watches. So in this case, this is the inside of a wristwatch, where you have this kind of spring system here in the center, which is basically collects mechanical energy, you could say, from the movement when you swing your arms, for example, and when it's spun up, you could say it will release all the energy from the spring into an electromagnetic generation, and with that charge some sort of energy storage. So, for example, a small battery. Or you can have these light switches for smart lamps, for example, called, in this case, it's called a tap switch, where you actually generate the power to send a wireless signal to turn on a lamp or turn off a lamp just by pushing the button that you want to turn on the lamp. So you basically have these wireless switches that you could put anywhere, and they're completely autonomous. Whenever you press a button, you generate enough energy to send a package, so to send a wireless signal to a lamp. So if we look into these examples, and if we look into generically, okay, what do you need then? What do these have in common? What are the basic building blocks of an energy harvesting system? We find basically these four building blocks here that you would find in any energy harvesting or energy autonomous system. So as a first, you have this energy source on the left-hand side, and basically this is the external source, as Wikipedia put it, right? So basically try to find a non-electrical source in the application's environment, that you could be converted into electric energy, and as basically indicated by some of these examples that I've shown you before. Typical examples for this energy source would be some sort of mechanical energy, so it could be some kinetic energy, for example, some vibration, some rotation. It could be a thermal energy, like in this watch that I showed you, the temperature difference between the skin and the air temperature. Or it could be radiant energies, which, for example, light or electromagnetic waves in general, electromagnetic fields like from your mobile phone communication or your Wi-Fi signal in the ambient environment. Once we have these energy sources, we of course then have to convert them into electrical energy, since this is what most of our electronic systems would need. And for this, we basically have this energy transducer as a second step. And energy transducers or energy converters, they would utilize some physical mechanisms that we can exploit to convert the energy, the non-electrical energy into the electrical domain. And typical examples here would be electromagnetic effects. So for example, the induction process in an electromagnetic circuit. We could have piezoelectric effect. So for example, we could have a crystal that if we push this together, the force applied will generate a voltage. For thermal energy, of course, we have the thermoelectric or Seebeck effect, where basically we transfer or we convert the thermal gradient or the thermal flow into an electric energy. And for photovoltaics, for example, we have the photoelectric effect, right? There are of course others as well, but these are quite popular ones. And then once we have converted this into, so basically we converted the non-electrical energy into electrical signal into an electrical domain, we typically need some further processing, here referred to as power management. This could be, for example, rectification. So if we have a electrical signal from our source that is alternating, we would need to rectify this to get a rectified DC current to our load. We typically talk about regulation. So we have, for example, want to have standard levels, or we want to have fixed levels, voltage levels to supply for our electrical load. We talk about matching. This could also be matching of voltage levels, but here mainly I'm talking about impedance matching to maximize the power transfer. And if we have, for example, an application where the source doesn't produce energy constantly, but we have an intermittent source. So for example, in a solar application, we have energy produced during the day, but we do not have energy produced during the night. We might have to have some charging of some sort of energy buffer in order to provide even energy to our load when there's no energy coming in from the source. And then, of course, as a last step, we have our electrical load. And our electrical load is, of course, basically the application or the system that sets the requirement on how much energy is needed and where, basically what to do with that energy. So if we look a little bit more into this electrical load idea, this creates a little bit of a challenge. So we can basically start thinking about what type of applications can we power with energy harvesting? So what type of applications can we make energy autonomous? And to do that, we can basically have a look into, okay, how much energy or how much power, in this case, do different applications require, right? And there are quite some differences between different applications, of course, different electronic systems. We have very power efficient systems here on the left hand side, where we have order of magnitudes of microwatt in average consumption. And here examples for this would, for example, be these these watches that we talked about, or calculators, typically very integrated type of systems with very specific tasks. On the right-hand side here instead, then we have these, let's say, more complex type of electronic systems, such as a normal personal computer that would have power requirements of the order of hundreds of watts. But then, of course, we have also systems like here in the middle. Right. So why is this a challenge? Well, of course, the challenge comes in when we talk about how much energy we can produce or how much power we can produce with our energy harvesting sources or these external sources. Right? And here, basically, we have the same thing, right? We have sources that produce very little power levels, so very low power levels, so in the order of microwatts. For example, ambient light indoors, if we give that to a photovoltaic cell, we will get very low energy. Or if we try to harvest from this kind of like electromagnetic fields, like from our Wi-Fi signal, for example. We of course also have some sources that can generate quite significant power levels, and maybe one typical example here would be photovoltaics outdoors, where we have strong sunlight. Or in the case when we have strong sunlight, we can actually generate, let's say, watts of power. But then we also have these sources that are in the middle. And of course, these variations here, how much power we get, these are very application specific. It depends on both the source, what, for example, in a thermal source, how much temperature difference do you have between the cold and the warm temperature, for example. But it also depends on your system implementation. So how large of a converter can you accept? So if you think about a photovoltaic, for example, the area of the photovoltaic cell that you could accept in your application, both maybe from the size perspective, but maybe also from a cost perspective. So basically here we start getting into this issue of, if we want to have an energy autonomous system, well, we have to match both sides. We have to match the producer, you could say, how much power we can generate, and we have to match that to the load, where we decide basically how much power is required. So to get a little bit more into detail for this, and to give you a little bit of a feeling what technical challenge and what solutions you could see, and how the process maybe of designing these type of systems look like, I would like to go into two examples for self-powered or energy autonomous embedded systems. One is a self-powered RPM sensor, so basically a sensor measuring the rotating speed of an object, of a rotating object, self-powered, so no external power supply. In this case, it should actually use the power from the rotation itself. And the second one is a self-powered pressure sensor, so basically the same idea of a sensor measuring a hydraulic pressure in a system, powered by some aspect of the hydraulic pressure itself. And both of these examples were included in a case study we've been working on the last years, together with Bosch Rexroth on hydraulic motors, in order to generate basically sensor devices, or to create proof of concept sensor devices that could be self-powered and provide information about the operation of the system. So at this point, I should probably also introduce you to two of our PhD students, Shu and Javier, who have been working quite extensively on these two example systems, and who stand for a lot of the practical work that I'm going to show you now. So if we start with a self-powered sensor system, as said, for the self-powered RPM sensor, we're interested in a system that can measure the rate of rotation of, in this case, a hydraulic motor, of whatever it rotates, powered itself by the some sort of energy that we extract from the rotation itself. And to do that, basically, the first step we can think about is where or what kind of conversion mechanism can we use to extract power from the rotation. And there are quite a number of different alternatives that we can use. But it turns out that there's one that is quite preferable for our case, at least, that works quite well at low rotational speeds, which are quite normal for these large hydraulic motors that we've been looking for. And this is called the variable reluctance principle, which is a form of electromagnetic transducer, so electromagnetic generator, you could say, some sort of electromagnetic conversion. So if you know about electromagnetic conversion, electromagnetic generators, for example, it would be quite common that you have a magnet, here shown in this blue-red box, and a coil that have a relative motion to each other. The variable reluctance principle is slightly different from the principle, of course, is similar. We still talk about electromagnetic induction, but in this case, both the magnet and the coil are static, so they stay at the same space. But we have this ferromagnetic wheel, like this metallic wheel, toothed wheel in this case, that rotates, so that is mounted on the rotating host, and this rotates them relatively to the static, what we call a pickup unit, so this magnet and pickup coil. And what happens then is, well, that because this is a ferromagnetic wheel, basically on rotation, we get alternating states between these teeth and these gaps aligned with this pickup unit. So, right, if this rotates, after a moment, you will have this gap under it. And this alteration between the tooth and the gap, this creates a change in the magnetic circuit, you could say, of this pickup unit, of this device, or so pickup unit and tooth wheel combined. And this magnetic circuit change, this leads into a changing flux, magnetic flux here in the center of the coil. And if you remember your physics classes from high school, if you have a change in flux in a coil, or basically in a loop in a closed loop of a wire, right? Then you induce a voltage to this, and basically since this is alternating, what we get as an output is this alternating voltage over time, right? So now that we basically then know that we can use a principle like this, we have decided on a principle for conversion. The next question, of course, is, okay, how much power could we get from this, right? So to do this, we basically designed one of these systems. We redesigned the pickup unit structure a little bit to optimize it a little bit more in order to maximize power output. But the principle is the same, right? We have this relative motion between the magnet coil structure and this tooth wheel. And basically what we can see is that, of course, the output power changes with rotating speed, right? The higher the rotation speed, the faster the change, the more flux change do you get, and that means you get a higher induced voltage, which gives you a higher power, right? So basically what we can see is, of course, this is basically maybe what we would expect. We get a higher output power with increasing rotational speed. But we can also, what may be more interesting to look at here, we can basically get a feeling about, okay, of what order of magnitude is this power level that we can get, right? And what we can basically get at low rotational speed that we were interested in is powers of the order of milliwatts up to tens of milliwatts in the higher range of these rotational speeds, right? So now that we then know how much power we can get from the transducer, how much power we can generate, then of course, like I said before, we have to link this to how much power do we actually need, right? And for this, of course, then we also designed a system. We looked into, like I said, a sensor system that should monitor that should sense the rotational speed of the object itself, or of the host itself. So we generated this, or we implemented this proof of concept system. We have a power management unit that, as you maybe remember, converts the energy that is generated, electrical energy, the electrical output that we get from the transducers or from the converter into something that is compatible with our load, our consumer, you could say. And our consumer, our load itself, is basically a very simple electronic system that has a gyroscope measuring the angular velocity, so basically measuring the rotational speed of our host. which is then read by basically this very small computer system, right? This is basically a microcomputer, microcontroller with a Bluetooth communication, so that we can read out the value, we can do some simple processing, and then we can send it, for example, to a mobile phone or some other Bluetooth host just to see the result. All right, so this is basically our experimental system, our load case. Here on the right-hand side, you basically see how much power this consumes during acquiring one of these sensor samples, right, the rotational samples. So basically what happens here, right, the sensor is asleep, basically consuming nothing. It wakes up, it starts reading or configuring and then reading from the gyroscope, so from the sensor, and then here in the end it performs a Bluetooth communication, and then it goes back to sleep, right? So we look at one sample acquisition here. What we can see here, maybe what is interesting is that the power level during sampling or during sensing is actually quite low, but it takes quite a long time relative to the communication period, where we have relatively high power consumption, power levels, but for relatively short amounts of time. Right. So for our load case in general, then it's maybe more interesting to look at this as an overall power consumption, so an average power consumption over time. And this is, of course, dependent on how many of these samples should we take, how often should we take a new sample, where we can basically see that, well, if we take one sample per second, we talk about power consumptions in the order of tens of microwatts, so close to 100 microwatts in this case. If we go for a second example here at 10 hertz, so 10 times per second we acquire a sample, we talk about 800 microwatts, close to a milliwatt, right? And of course, this goes up the faster you sample, the more data you want to acquire. So if we remember now, okay, we have this energy generators that can give us basically milliwatts to tens of milliwatts of power, and we have our sensor system that, depending on the sample rate, of course, requires microwatts to hundreds of microwatts of power, maybe to milliwatts of power, depending on how far you want to go with the sample rate. This already looks quite good, right? So basically, this we can just confirm by putting this into a complete system. So here basically have an implementation of the system on a test setup, where we basically here have this harvester with the coil and the magnets that would sit here and rotate with the host. We have the sensor unit here with the power management and the sampling and so on the basically the electronic load, right? And then basically on rotation we can measure how much power we actually supply to our load, and what sample rate, so how many samples we could acquire per second as a result. And this is basically what is shown here on the right-hand side. So here you have this power output over different rotational speeds. In this case now after the power management, so this has basically taken consideration for all the losses that we would have for converting these power levels. And basically here on the bottom, then you see what sample rate would this power represent for our sensor system. So how many samples can we acquire at different rotational speeds? Okay, so having a look at the second example, right? If you remember, with the second example is a self-powered pressure sensor. And again, here we wanted to investigate, can we actually use the pressure itself, the pressure signal itself to power the sensor. As it turns out, the pressure, ideally we would expect a static pressure in our hydraulic system, but in fact there is a variation. So there's a fluctuation on this pressure signal, typically generated by pumps or other systems components in the hydraulic system, generating basically a time varying pressure signal that fluctuates around the static pressure that we want to have for the hydraulic motors operation or the hydraulic systems operation. So how could we convert this pressure fluctuation? Well, this green blob here that you see, this basically represents a piezoelectric device, a piezoelectric crystal, you could say, or a device constructor of piezoelectric crystal, which basically, when you apply a force to it, generates a charge, right? And basically generates thus an electrical output proportional to the force that you apply here. And since we have these pressure fluctuations here in the system, basically what we do is we convert this fluctuation into a alternating force onto our crystal here, and then basically we can extract a electric output from this crystal, right? Again, an alternating electric output. Now, if we compare this to the previous case, the rotating energy harvester, the signal in this pressure wave becomes a little bit more complex. So this is actually a example or a data log from how the pressure signal looks like in this hydraulic motor that we have been working with. On the top here, you see the time domain, and already here we can see, okay, it looks a little bit chaotic, but we could assume some sort of periodicity in this, which becomes much more clear when we look in the frequency domain, when we convert this into basically what type of frequency components does this signal consist of. And there we can basically see we have, of course, a number of different factors, but we have a few strong contributors, you could say, right? So we have at specific, we could say, frequencies, strong signals that provide us a certain pressure amplitude, right? Now for an application, this is interesting, of course, because now we have to think about, or we can utilize this to think about how can we exploit these contributions, and how can we tune our harvester to specific frequencies in the system. And one thing that we can do, and what we have done, is we have been looking at methods to improve or basically to amplify specific frequency components. In this case, we can use acoustic resonance for this. So this is basically an acoustic resonator. You can think a little bit about your case, when you blow into a bottle, and at a specific rate of blowing, you get basically a specific tone out of your bottle, right? Creating basically this resonance in the chamber, you could say, right? And this basically is the same kind of structure, right? You have this volumetric chamber here, which is hollow, and you have this neck. And based on basically the volume of this chamber and on the length of the neck, we can basically define which frequency, at which frequency we want to have a resonance behavior, which we basically see here on the right-hand side, right? We basically see that in this case, it was for 200 hertz, optimized for 200 hertz resonance, and we get this typical resonating behavior that we get a power peak, you could say, or a signal peak around the resonance frequency, and this kind of bandwidth around it, where if we go further away from the resonance frequency, our signal will break in, right? So this basically allows us to focus on, in this case, and specifically, let's say a 200 hertz signal, amplifying the reaction of our system to this specific excitation. And again, of course, then we can build a full system out of this. Our self-powered pressure sensor, where we basically here would be our pressure signal connected. So we basically get our force in. We have here this resonating chamber that will amplify our force at a specific frequency excitation, which will then press onto this piezoelectric stack in this case, which generates the power for our electronics and our sensor. Right, and again, here we can basically then see that this is, of course, the power output is then, of course, proportional to the amplitude. This would be for a fixed excitation frequency of 200 hertz now, where we basically get, with higher amplitude, a higher power. And here on the right-hand side, we're basically at the the sample frequency that would be a result of this power. How often could we read the sensor based on the power that we generate? And again, we talk about, well, micro watt to milliwatt, depending on your pressure amplitude. Okay, so just to summarize shortly some of these technical challenges that I've been talking about based on these examples, to create basically these successful, you could say, energy autonomous sensor systems or embedded systems. Like I said, we have to start with thinking about, we have to match available energy and required energy. We always, for this energy autonomous operations, have to find the right amount of energy or reduce our requirement to match the available energy. So here we have to lead to a, you could say, a matching situation between available and required energy. Something I haven't talked about so much, but I just mentioned it a little bit in the sentences, since I wanted to avoid a lot of technical circuits. But one important thing is to minimize conversion losses. So this would be in the power management. We want, of course, since we have a limited amount of available energy from the harvester, from the external source, we want to make as much of this available to the load and not lose a lot of this in conversion steps. We have to think about that the energy contributions, the energy signal, is dependent on applications. So typical example here was from this hydraulic pressure spectrum that I shown you, that of course the frequency and amplitude components, they will be dependent on different application cases and different system configurations. And in order to basically match this first step, we have to be very careful with our load system design. So basically, we have to optimize our sensor systems or embedded systems so that they actually get into this order of magnitude of microwatts to milliwatts that we can generate or expect from ambient sources. So I would like to conclude with some open challenges, you could say, or some trends, some questions that go forward, you could say, in research on energy autonomous and energy harvesting systems. So if you look at research right now in energy harvesting, quite a lot of focus has been on output power. A lot of this, what I've shown you today, was basically, it's the big question, you could say, in energy harvesting, right, or in energy autonomous systems. How do we get to match the source with the required level? How do we close this power gap? How do we do something useful with it? But I see that, I mean, now that we basically show more and more systems where this works, we also have to get into other questions related to this, which maybe have more to do with being able to predict how much power you could expect in different applications, to scale the same solutions to different applications, and to do, you could say, true comparisons between different solutions to be able to evaluate them under similar conditions. The second point here is that existing research so far has been focused quite a lot on individual components. So basically on parts of the system that I showed you today, to either optimize, for example, power production, or optimize power management, or optimize the consumption. But that we see a value that in the future there has to be much more work on this kind of trade-offs in the system. What happens if you connect one of these components to another, and is it then really the best to optimize each component individually, or do you have to optimize on a much more holistic level? And finally, there have been, of course, systems similar, as I showed you today. There have been implementations of full systems that do something useful. But if we want to see that these systems get out from research and get more into, let's say, real industry applications or real useful applications outside of academia, then besides these demonstrations of individual proof of concept systems, we also have to work much more with systematic design tools and methodologies to implement and to make these kind of systems reproducible and simpler to design. Well, and with this, I would like